Hi everyone, in this video we'll be going over section 2.6, which is about limits at infinity. Main focus in this is going to be horizontal asymptotes. So this section will be somewhat similar to section 2.3 in that we're going to have to really rely on our algebra and our prerequisite skills, and it also adds one little part to horizontal asymptotes. So when you recognize horizontal asymptotes, it can be helpful for these type of questions as well. All right, so let's get into it. When we're looking at limits that where x approaches infinity or negative infinity, so for example, we would write the limit as x goes to infinity of f of x equals L. This really means as x gets bigger and bigger and bigger and bigger, what's happening to the function. So the key thing here is if the function is bound by something, meaning the y's can't go up, or similarly, let's say you're bound down here and the y's can't go down as x gets larger, so as it moves to the right in the positive direction, then you know you have some type of bound, some type of limit. So in that case, you would say that limit equals to L, where L is some y value. Similarly, if your x's are getting sufficiently more negative, so going off into the left-hand direction, if they're bound by something here or bound by something here, then we know that they're limited. So what we have to do is figure out, okay, well, what does this look like graphically, which I sort of showed you now, but I'll draw it out too. And from there, we have to think, well, what can we do computationally to help ourselves with this? So there's some extra, I would call them tricks, but extra little steps and things you can do in there to help you out. What it's going to take is a combination of your algebra skills, being able to recognize what to do and when, and an intuitive understanding of what's going on, which we talked about, I think it was in section 2.2. So let's go ahead and look at this visually, and then we'll do a few algebraic examples. All right, so visually, the key thing to take note of are horizontal asymptotes. That's because horizontal asymptotes bound us in the vertical, or we could say the y direction. All right, so I will give a few different examples here. So let's say we have a little plot, and this doesn't have to be nicely drawn. We're just getting the idea across. So mine certainly isn't going to be lovely, but it'll suffice. All right, so let's say we have some horizontal asymptote here, and I'm just going to name it as y equals L, so I'm being consistent with the limit notation that I already have. And let's say we have some function, and this function is coming from up here and going down this way. Whoa, it's not drawing. Going down this way to the left, and that's meant to be following along that little axis. So in here, right, so in this, since we're just looking as this goes off to the left, the way we would denote it is the limit as x goes to negative infinity of f of x is equal to L. And this can take all different shapes, all different forms, so I'll draw a few more out just so you get the idea. So let's say we have another one. Draw that out, and this time let's have a little asymptote down here. So here y equals L, and let's say we have a function coming like this and then going along that asymptote. In this, we would say the limit as x goes to infinity, because we're moving to the right with an arrow here, of f of x equals to L. So it's equal to L because it's bounded in the vertical direction by this horizontal asymptote. I'll do a couple more. So let's say have something like this, and I don't know, let's go this way. All right, so now we move it up here. Let's say we have y equals L here. Okay, and maybe this hops around a bunch, but then as it goes off to infinity, it's still bounded by L. So in this case, we have the limit as x goes to positive infinity of f of x equals L. All right, so hopefully with these, we can see why taking note of these horizontal asymptotes and where they are is important. All right, so let's move on to the computational parts of this. It's going to get a little bit more tricky here. It is going to take some foresight on your part, and it is going to take a little bit of intuitive understanding. But there is one nice thing, and that's if you remember prereqs, sometimes you can move through this a little bit more smoothly or quickly. So looking at this, we want to calculate the limit as x goes to infinity of 3 plus 2x divided by 2 minus x. All right, really key thing that's going to help you out a lot if you remember from pre-calc is when horizontal asymptotes exist. So if you were in class, I'd have you work together and I'd say, oh, can you remember this, recall this? But since you're not in class, I'll just tell you, I suppose. So let's note that, or I should say recall that. Okay, when the degree is the same, the degree is the same on the top and bottom, or on the numerator and denominator, if we're being a little bit more formal, on the numerator and the denominator of our function. Okay, a horizontal asymptote exists at y equals the lead coefficient of each part. So the lead coefficient of the top over the lead coefficient of the bottom. All right, so in our example, I actually know there's a horizontal asymptote right now. So in our example, all right, I can see that my degree on both the top and the bottom is 1. If you've forgotten what a degree is, that's just the largest exponent that your variable is raised to. So since x in both the top and the bottom of this is raised to the first power, the degree is the same. So I know that since the degree is the same, okay, there is a horizontal asymptote at y equals, all right, the lead coefficient is just the number in front of the variable of the highest degree. So in the numerator, that's 2. In the denominator, that's a -1. Okay, so I know I have a horizontal asymptote at y equals -2, right? This means the limit as x goes to infinity of 3 plus 2x over 2 minus x is equal to -2. And that goes back to those visuals we looked at and the significance of those horizontal asymptotes. So honestly, if you're going through a question and you notice this right away, and you write something like this as your answer, so you explain it thoroughly and show me that you understand the importance of this horizontal asymptote, you're done. However, let's say you don't notice this or you just like to do things algebraically, you can absolutely go through this process using algebra. So I'll do it that way just to give you an idea of what it looks like. So let's say that instead you decide to use algebra. Okay, you'd have to consider the limit as x goes to infinity of 3 plus 2x over 2 minus x. Oh, that's not a good looking minus sign. Over 2 minus x. Okay, so if you think about running this limit through right now, you'd get 3 plus 2 times infinity and 2 minus infinity. That isn't something that we call indeterminate form. I actually noticed this in some homework assignments. People would write, oh, infinity over infinity, so it's 1. Well, you can't really divide infinity out, and you can't really multiply something by infinity. If you think about it, infinity is not a regular number. It doesn't stop anywhere. So if you're saying, oh, it goes to infinity, well, it could be 3, it could be 4, it could be 1,000,000, it could be 1,000,000,000. So how can you say that 1,000,000,000 divided by something that could possibly be 2 is equal to 1? It just simply doesn't work. So little math history, they made the infinity symbol to be able to talk about things like this and represent it with something, but it does not follow the process of regular natural numbers. So when you run a limit through and see that you have something with infinity over something with infinity, you can't just say that it's 1 or -1. You have to put it into a form where you know for sure what is going on. This is what we're going to try to do algebraically. So I'll give you some tips. We'll go through it. Hopefully it'll make sense. All right, so in this, like I said, it's not helpful to run through this right now. However, we should remember that if we have, and I'm going to erase this in a minute, something like 1 over x, we know where this goes, right? The 1 over x graph looks something like this and like this. So if it goes off to infinity, we know there's an asymptote at 0, so the limit is 0. If it goes to -infinity, there's an asymptote at y equals 0, so it goes to 0. Thinking about this computationally, if x gets bigger and bigger and bigger, we'd have like a 1/2, gets bigger, a 1/3, bigger, a 1/4, bigger, a 1/5. We can see that my decimal equivalence gets smaller and smaller and smaller. So essentially, as you divide by a larger number, your whole fraction is going to go to 0. Okay, so that's what's going on with this. That is what we're going to utilize when we're working through these problems. All right, so I went ahead and typed out what I just said verbally and also summarized it a little bit. So basic idea is if you can get more of these fractions inside of your function built in there, and this is only true when you have x going to infinity or negative infinity, but if you can get that in there, it helps you determine what's going on. So your goal is to get more fractions. The way you do this is multiply both the numerator and the denominator by 1 over usually your variable to the highest power that's in your function. So sometimes that changes. You'll know because you'll do that step and realize that doesn't help you at all. So you might have to play around with it by choosing a different degree in what you multiply by, but generally it's going to be a good step if you have x going to infinity or negative infinity. All right, so kind of hard to understand that verbally. Let's go ahead and see what this looks like computationally. All right, so in here, I already noticed that. The degree of both the numerator and the denominator of this is 1. So I'm going to multiply the top by 1 over x and the bottom by 1 over x. Now keep in mind it's important to do this to both the top and the bottom. The reason for that being is when I multiply by 1 over x divided by 1 over x, this is really the same thing as 1. It divides out to 1. So I'm not changing my expression at all. I'm keeping it the same, which means it's completely mathematically legal. Sometimes people will just multiply by a 1 over x. You don't want to do that because then you're changing the expression you're working with completely, which is a fairly large conceptual error. All right, so I'll scroll down here just a little bit. Okay, if I do that, what I end up getting is the limit as x goes to infinity of 3 over x, so I'm just distributing this through, plus 2 over x, all divided by, distributing in the denominator now, 2 over x minus x over x. Doing some simplification here, I have the limit as x goes to infinity of 3 over x plus 2x over x is just 2, all divided by 2 over x minus x over x is just 1. All right, so when I see this personally, I'm like, oh yes, I've taken good moves because I know the limit of any constant, for example, 2 and negative 1, is always going to be that constant. That means I can absolutely calculate that limit. It's not an indeterminate form anymore. Now, looking at 3 over x and the 2 over x, I know as x goes to infinity, aka the denominator gets bigger and bigger and bigger. My numerator is staying as some constant, so this will certainly go to 0 for the reasons that I described previously. This means I can now successfully run my limit. So running this limit through, all right, I see that, discussed this already, the 3 over x is going to go to 0, the 2 over x is going to go to the 0. I know that the 2 and the negative 1 are constants, they just go to themselves. So what I end up getting is 2 over negative 1. That is negative 2 for our final answer. Should you be surprised by that? Absolutely not. Remember, we talked about this before. We said, since there's a horizontal asymptote at negative 2, that is going to be my limit. Well, now you've just done a fair bit more work to confirm that. So, like I said, 4 things, if you can notice there's a horizontal asymptote right away, it's going to save you a lot of work. But if you don't notice it, it's okay because you can still use algebra. A little disclaimer, I think the WebAssign might make you use algebra every time. I'm not sure about that, but you might have to. For me, on assessments, if you choose to just use the knowledge of a horizontal asymptote, you just need to do something like what I wrote in the green here and thoroughly explain so I know that you understand the concept and why it's true. Okay, let's try another one. This one will be a little bit more tricky, but similar idea. All right, so if we start this the same way and we're like, okay, well, let's run my limit as x goes to infinity through. Notice that you'll get infinity on top, x squared. That's kind of like infinity squared, which is just an even bigger infinity. And then in the bottom, you get root of infinity, which is still going to be infinity. So it is definitely an indeterminate form. You can't run the limit right now, which means you need to find some algebra to see if you can work through this. All right, another interesting thing here is to take note that in terms of a degree, okay, in the denominator, I have the square root of x to the fourth plus 1. Right, we can't just peel square roots apart, so don't write this down, but some people write, oh, x to the fourth plus root 1. Okay, you can't just pull a root apart like that. It's all included underneath that. So we're not going to do that, but we can say, well, we know what the degree is. So here I can certainly conclude that the degree, right, is 2. And that's because the square root of x squared is 2, or sorry, square root of x to the fourth is 2. So the degree is 2. So in here, I actually know that the degree in both the numerator and the denominator match. So if I wanted to, I could say, since the degree in the numerator and the denominator match, okay, I know my horizontal asymptote is at y equals, okay, the lead coefficient in front of the numerator is 1 over lead coefficient in front of the denominator is root 1, which is really just 1. Thus, I already know that the limit is at or is equal to 1. However, you're not always going to be able to rely on this little trick. Sometimes you'll have to use algebra, so I'm still going to show you the algebraic process for completing a question like this. It is a little bit more tricky than what we did previously. All right, so algebraically, right, we have the limit as x goes to infinity of x squared over root x to the fourth plus 1. Right, if we're in class, I would say, oh, what do you think we should start with? What do you think we should do next? And some people, maybe yourself included, could think of the answer, which hopefully you're doing right now. And the answer would be to use a similar trick as to what we did last time. So I noticed that in this question, the highest degree is x squared. So what I'm going to try first, and hope it works, is to multiply both the numerator and the denominator by 1 over x squared. All right, so when I do that for the numerator, which is the more gentle part in this question, I get x squared over x squared, which is just 1. All right, the denominator is a little bit more tricky, okay? So I'm going to write this out. I have root x to the fourth plus 1 over x squared. All right, so some students will accidentally shove this x squared up into the square root. You can't do that. This x squared is not underneath the square root. The x to the fourth plus 1 is. So the first thing you have to do, write this out, is you must get x squared under the square root as well. Okay, you need like terms. All right, I'm going to erase this, but if you want, you can fast forward through this, but I'm going to give you a brief algebra reminder just in case you don't remember why that's so. All right, so briefly, like I said, I'll erase this. If we have root x to the fourth plus 1 over x squared, this is the same as x to the fourth plus 1 to the 1/2, so a square root is the same as raising something to the 1/2, over x squared. All right, notice here that your exponents do not match, so you can't just push these things together. However, I could write this, x to the fourth plus 1 to the 1/2 over x to the fourth raised to the 1/2. So notice that properties of exponents tell us when we have a power raised to a power, we can multiply the exponents. Well, 4 times 1/2 is in fact equal to 2. So these are equivalent statements. Now that my exponents, the 1/2 and the 1/2, match, I can push this all into one fraction. So this is equivalent to x to the fourth plus 1 over x to the fourth all to the 1/2. Properties of exponents say when you have a fraction divided, you can apply that exponent to both terms. So I'm going to use this concept to write my limit in such a way that I can get my x squared underneath the square root. All right, so using that concept, what we have is the limit as x goes to infinity of 1 over root x to the fourth plus 1 over square root of x to the fourth. Remember, x squared is the same as square root of x to the fourth. Okay, so I'll even write that up here just for clarification. Root of x to the fourth equals x squared. So I'm going to substitute. That's what I just did there. All right, substituted the x squared for root x to the fourth because they're the same thing. Okay, now since I have a root and a root, meaning I have like terms, those two things are matching, I can push this into one fraction. So I have the limit as x goes to infinity of 1 over big square root of x to the fourth plus 1 over x to the fourth. Right? Since I have a common denominator here, I can split this again. I'm showing a lot of steps here, but I found out oftentimes students will kind of forget the algebra, so it's probably a good thing too. Okay, so we have 1 over big square root of x to the fourth over x to the fourth plus 1 over x to the fourth. So since these are over a common denominator, you can split that fraction up. That only happens if you have a common denominator. All right, and finally, this is equal to the limit as x goes to infinity of 1 over square root of x to the fourth over x to the fourth is just 1 plus 1 over x to the fourth. All right, now in my head, I'm thinking, oh, that was a lot of work. However, I'm happy. It was a fun little puzzle, and it looks like I reached the point where I can actually draw a conclusion. So, looking at the top here, I know the limit of any constant is just itself, so I know that's 1. Recalling the limit laws, I know I can run limits underneath square roots, so running that under the square root, the limit of 1 is, of course, just 1. And I should recall from previously in these notes, or maybe previous classes, that when I divide a tiny constant by something that's getting huge, x to the fourth is getting huge because it's going to infinity, that's going to go to 0. All right, so this leaves our final answer as 1 over root 1, which is 1. And again, that's exactly what we anticipated based on the horizontal asymptote that we discussed previously.